Okay, I think we'll get started. So fun lab today. We're going to continue with our analog to digital conversion with the PIC12F675 microcontroller. And what we're going to do here is we're going to read in an analog signal and convert that to a pulse width of an on or off of the pin. So we'll be able to do some pulse width modulation based on the voltage that comes in. So we'll dial in the voltage and we'll control the amount of on in the duty cycle and the amount of off in the duty cycle. So how we're going to do this, very simple setup. And again, the idea here for this series is to not so much worry about the electronic setup, but just try to find the simplest setup that will demonstrate the different aspects of the PIC controller itself and then the assembly code that goes along with programming that. So we're going to set our GP 0 pin into analog mode and then our GP2 pin into digital output mode, and we're gonna just have a simple trim pot here for a voltage divider to give us an input signal, and then we will send the output signal to a scope. We'll also have it on a LED, so we'll be able to see that get brighter or dimmer depending on how much during the duty cycle is the pin on versus the pin off. All right, so let's get right to that. So I'll switch here just to show the dock cam first. So setup is very simple. Got the voltage divider here. I don't have it plugged in yet because we're going to program the microcontroller, and I don't like to have the input voltages on when I'm using the PIC kit as the power supply. Then we will remove the PIC kit and supply with just an outside supply from a USB. The LED is here, and then we have two leads here. These are going to go to oscilloscope, and I'll move my camera to see the oscilloscope later when we go. All right, so let's look at the code for this. Oops, let's see. So this is, yeah, okay. So I guess I have this. This is not the coin flip program. This is the Pulse Width Modulation program. All right, so everything here is all the same. This is the configuration bits. Here is the include file, then the reset vector, so where the program is going to tell the program counter to start. And then, as always, we have the main and then main loop, main being all the stuff we have to set up only once, and then the main loop being what continuously goes with the microcontroller. All right, so we've done this, if you've been following through the lab series, we've done this a lot now, so I'll go fairly quickly through this. But we need to shift to bank 0 so that we can talk to the GPIO. We clear that for good measure. We'll deal with the comparators by just turning that all to zeros because we don't want to use the comparator. We're using the analog to digital. That sits on bank 1, the AND-cell register, so we have to use the status register, bit 5, to shift over to bank 1. And then we will use the, and maybe I will show this here just as a reminder if you haven't, if this is the first video that you're seeing. So if you follow along on your data sheet, we're going to be loading the AND-cell register here, and so the last 4 are telling us what we want as inputs, and so we just want GP0 as the analog input. The rest will remain in their digital capacity, and then the first bit is not used, but then these 3 bits are used for the clock speed of the analog to digital conversion. So as we look here, we're just going to use the internal clock, and so it doesn't matter what bit 6 is, but these two need to be 1s here. Then that's sent to the AND cell, and now we have to set up the tris. So we want pin 1 as an input. Even though you're doing analog rather than digital, you still have to set the tris as an input pin. We want pin 2 to be an output pin, so that's 0. It doesn't matter what the rest are for this particular program. Then we need to switch back to bank 0 because we're going to be controlling the GPIO pins in the main program, and that's on bank 0. Then some of the extra stuff we need for the A to D. We need to fill the A to D on register, and so that's on page 43 here. So if we look at this, we are setting this first bit to 0, and that's this one here. That's going to tell us, are we right justified or left justified, and that's over here on page 42, meaning that we're going to set it to 0, so that means our most significant bit is going to be bit 7 of the A to D res H, and then the least significant bit is going to be bit 6 of A to D res L. We need 2 registers because it's a 10-bit converter, and rather than an 8-bit converter. Then the right justified case is over here, and we're not using that, but that would be if we put a 1 in this position up here. All right, then we're going to make sure that we start with our digital output pin as off. Then what this does, this starts the A to D cycle, and so it will begin the cycle, so this is necessary to start the acquisition. Very minimal code though, and you get an acquisition there. Then we set. So what we're going to do here is we're going to read in the voltage. So that's what's going to happen here. Then it's going to set the pin. And what we're going to do here is we're going to move the high res. So we're just going to focus on the 8 bits. And that'll be enough for this pulse width modulation. We don't need all 10. So we're just going to focus on the the most significant 8 bits. And we're going to move this to the working register. So the move F, here's the register. This 0 means we're going to move it to the working register. If it was a 1, it would just move it back into this, which wouldn't be what we would want to do. The way our voltage is set up in the divider, we can't bring the voltage all the way down to 0. So what we're going to do is we're going to subtract a little number to drop down, to effectively drop our voltage so that the lowest voltage, the minimum voltage, reads 0. We're going to give ourselves a little buffer here because there's fluctuations, and if we go below 0, then the register rolls over and it's as if we have a really large number. So when we would calculate this, and I won't go through this, we would calculate a 51 here, but I'm going to just put a 43, which would correspond to a 0.8 volts. Our lowest voltage we can get is about 1 volt. Now, the way the subtraction works is it subtracts the working register from the literal. So that's not what we want. So we have to do a little bit of fancy footwork here to get that switched around. So we're going to move the result into, so this is going to subtract the working from the literal and then put it back in the working. We're going to then put that into some storage register. We'll just use B2, that's not being used here. And then we need to take the 2's complement of B's 2. So that's essentially taking the negative of that. So we have number minus working, and we wanted working minus number. So if we take the 2's complement of that, then we get this. The 0 here means we're going to put that back in the working register. So the working register has gone from the full voltage to the negative of the voltage minus this offset, then that's been complemented around, so that's positive, and that's what we want. And then this is now in the current working register. So when we are at our lowest voltage, this should be almost zero. A little bit of a buffer there to give us a little room for fluctuations that go below zero. Then that will call the delay. So if our voltage is very low, then the delay will be small. If our voltage is big, the delay will be bigger. We have only a single nested loop, so this is at most 256 clock cycles, and we're going to just have one fraction of that being the on, one fraction being off, depending on how much voltage we're giving the analog input. So if we turn our voltage all the way down, then a very small amount of that is going to be on and most will be off. And if we turn it all the way up, then a large amount will be on and most will be off. Okay, so then we switch to off. So we're on for whatever the delay is, we switch to off, and what we want to do is take the rest of that duty cycle as off. So it's going to depend on what value of the voltage we have, but we're going to subtract that from the maximum, which will be 255 here. And then we're going to add, so this again, this adds just a small number here as a little buffer for fluctuations so that we don't roll the register over into the negative, and then we get exactly the opposite of what we want. So between these two sets here, we control the amount of the duty cycle, the 256 computer action clock cycles where we're on versus off. And then we just go back to our main loop. So a fairly simple program. So let's go ahead and build this. And then let's go ahead and set this to the chip. Okay. And now I'm going to go to the full, we don't need the code anymore, so I'm going to go over here to the doc, just to the doc cam. And then I'm going to move the picture of me over to the more important thing, the oscilloscope. Let's see. Okay, so I'm going to now remove the PIC12F675 and I'm going to plug in the voltage from the voltage divider, and then we're going to run and I'm going to turn on the voltmeter here too so you can see that. Okay, let me see. Okay, so sorry for the cords here. So now we will, I lost my screwdriver. Where did I put that? Well, I'll try to use my fingers here. I better get that screwdriver. All right, I'm going to pause the video and find the screwdriver. Okay, so found that screwdriver. Let's watch now. The voltage is low here, and we can see on the oscilloscope that our duty cycle is largely low. And now I'm going to turn the voltage up, and we see an increasing amount of time of that duty cycle being on. And now we're all the way up, and now we're mostly on in that duty cycle. Now also pay attention to the LED that's hooked up here. So now we're mostly on, so we're turning the LED on most of the 255 cycles or 256 cycles. Now we'll turn this down, and you should see, it's hard to see on the camera, I guess, but hopefully you can see. I'll try to do it back and forth here. You can see the brightness of that LED changing. All right, so that is the pulse width modulation controlled by a voltage. As a little challenge, maybe what you can do here is see if you can write a code to have a voltage controlled frequency. So try to change the frequency at which it goes on and off as a function of the input voltage.